Assalamu alaikum warahmatullahi wabarakatuh. So this is a video lecture of digital signal processing. So we'll be mostly discussing theoretical topics. Through slides, video lectures, because it's not technically possible for me to discuss mathematical topics with the help of video lecture. So what I'll be doing, I'll be covering mostly the theoretical topics now, inshallah ta'ala, when things will get back to normal and your college will be functional. We'll be discussing mathematical topics as well as the numericals that are involved. So let's begin. So basically, your entire syllabus of DSP is categorized into these uh, topics. In your first chapter, we'll be discussing signals and systems. That's that you must have studied in a third unit, followed by DSP and FFT, discrete Fourier transform and fast Fourier transform. And it's very important, the signals and systems, that's in your gate as well. So the gate students, for them, you must have studied this first unit. So it will be just a revision what you have studied in third semester. Fine. So DFT, discrete, I hope it's new. Fast Fourier transform, it's also, I guess, new. Then designing of IR filters and finite infinite filters. Then followed by the applications of digital signal processing. So this is your entire curriculum of DSP that's divided into these categories. So your entire syllabus will be covered accordingly. So mostly I'll cover, I'm again telling you, I'll cover only theoretical topics for now. Mathematical topics and numericals I'll be discussing in the class hopefully soon. Right? Okay, so these are the books recommended. You can also, you can see it, you can Google it, or you can check your syllabus that's available on the university website and see the books that are available. So those of you who are not uh, comfortable with foreign authors, there are some Indian authors available as well. So they can Google it out. There's Sanjay Sharma and all. But Sanjay Sharma has some mistakes in it. So there are some printing errors. I will not call it mistakes. There are some printing errors. So you can go through them as well. So let's begin. Okay. So first, we'll be discussing what is the need of DSP. Why? What is DSP? What is digital signal processing? What are the needs that we need to digital process a signal? Fine. Now, digital signal processing, it's very common today. You know, everybody of us is directly or indirectly involved in digital signal processing and its applications. Right? Now, the subject of digital signal processing is mainly related to electronics and computer engineering. Fine. The signal processing takes place. Forget about analog and digital. Fine. It takes place in amplifiers, in attenuators. It takes place or in transformers. You have filters, transmission lines, channels, etc. Fine. Now, what is difference between analog signal processing and digital signal processing? Fine. Uh, when a signal is analog, it's analog signal processing. When a signal is digital in nature, it's digital signal processing. Now, all of us know that a computer is a digital machine. Thus, any type of signal processing is done by computers is basically a digital signal processing. So, any type of signal processing that is done by computers is basically a digital signal processing. Fine. So, this is the need of DSP, the digital signal processing. Next, I'll be discussing what are the advantages of DSP over analog signal processing. So why we go for digital signal processing instead of analog signal processing? Now first, you know that your digital signal process, like I have discussed here, they are more flexible. What do you mean? So what do you mean by flexibility? That is, the system can be configured for some other operations by simply changing the software program. So any examples that you can think of? For example, the high pass filter can be changed to a low pass digital filter by simply changing the software. So it's more flexible. You just need to change the software and you can convert the high pass digital filter into low pass digital filter. So you don't need to go for any changes in the hardware. Okay? So the digital signal processing systems are high. This makes them highly flexible. So such type of change is not possible in analog systems. Fine. Next you have the accuracy. So accuracy of digital processing systems than is much higher than analog systems. The analog systems suffer from component tolerances, like you have breakdown, etc. Fine. Hence, it's difficult to attain. You have a high accuracy in analog systems. The digital signals can be easily stored on storage media. Next is the storage, right? So the digital signal can be easily stored on storage media such as you have magnetic tape, discs, etc. Whereas in analog signals, you suffer from storage problem. You can't store them like noise, distortion, etc. Hence, digital signals, because you can easily store them, they are easily transportable compared to analog signals. Thus, remote signals of the remote processing, of digital signals is possible compared to analog signals. Fine. Then you have mathematical implementation is simpler. Fine. In mathematical, you can implement digital systems can be accurately performed on digital systems compared to analog signals. So you can perform the see why I am discussing uh, digital DSP or ASP. These are basically the advantages of digital signals over analog signals. Fine, because digital signal processing involves digital signals, whereas analog systems involve analog systems. So that's why I am discussing DSP or AC. Basically, we are also discussing the advantage. So those of you who are familiar with the advantages of digital signals, our analog systems, for them is just a repetition. Next, you have the cost factor. So, uh, so they are cheaper as compared to analog systems. Right? Clear? So flexibility, accuracy, these are the advantages of digital signals over analog systems. They are more flexible, they are more accurate, storage is easier, mathematical implementation is simple, and they are cheaper. Then you have easily upgradable. Since they are why they are easily upgradable? Because they are software controlled. Fine. Then you have universal compatibility of digital signals, and also the size system that's involved is smaller as compared to they have more rugged construction, robust construction of digital signals. Digital signal processing systems have more robust construction, rigid construction. Okay, so they are small in size. So there are digital signals also suffer from some disadvantages. Those of you are some familiar with sampling and all, right? Or you have discussed or you have studied digital signals. So they have also some disadvantages, like they are not suitable for analog signals having wide bandwidth. Why? When analog signals have wide bandwidth, then high-speed analog digital converters are required. What are analog digital, which convert an analog signal into digital signal? Such high speed of analog digital conversion are difficult to achieve for same signals. Right? So for such applications, analog systems must be used. Again, DSP. Next, the DSP systems are expensive for small applications. Hence, selection is done on the basis of cost, complexity, and performance. So, what these are the applications? This is the most theoretical part. So you can Google it up. There's nothing much to be discussed here, or to be there's little scope left to discuss. Fine, this is just theoretical. So I'm just giving you the idea of it. Then you have the applications of DSP in speech and voice recognition. For example, you have you have speech and voice recognition. You have number one application. So in speech recognition, you have voicemail, speech, speaker verification, speech enhancement, speech synthesis, text to speech, etc. Right? It's also used in the field of telecommunications. You have cellular phones, speaker phones, digital speech interpolations, or you have video conferencing, express spectrum communications. Fine, it's all used in the field of telecommunications. You have packet switching, or you have channel multiplexing is also there. Fine. So it's also used in the field of consumer applications, digital audio, video, television, music systems, etc. Right? Or you have toys for kids. Right? Then you have graphic and imaging. You have 2D and 3D visualization, pattern recognition, image transmission, and compression enhancement, robot vision, satellite imaging for multi-purpose applications. Fine. You have radar processing, sonar processing, military in the military and defense. Right. You have navigation missiles, RF modem secure. It's also used in the biomedical engineering. You have X-ray storage, enhancement, ultrasound equipment. Diagnosis and tools. It's also used in the field of industrial applications. Fine. In the field of instrumentation. Fine. For control applications. For automotive. What are automotive applications? Yes. So these are vibration analysis, voice commands, digital radio, engine radio, navigation, cellular telephone, voice cancellations, adaptive ride control, etc. These are the DSP has wide range of applications, right? We'll be discussing some of the applications in the last chapter, last topic. Now, just a sec. Now, after applications, now we have to next is see the various technology that is used for DSP. One is the dedicated processor systems, processor based DSPs. So either dedicated processor based DSPs are used, or general purpose based DSPs are used. In dedicated processor based DSPs, you have analog devices like you have ADSP 21XX series, or you have text instruments, TMS, or you have Motorola also is also there. So these DSP processors, the dedicated base DSP processors, are specifically designed for array operations, like and multiply accumulative operations. So they are basically used for array operations. Fine. Then you have the general purpose base DSP. So in this, software is used to perform DSP operations on a computers. Fine. Like you have a C program can be developed for digital filtering, or you have Z transform or Fourier transform FFT, which runs on computers. Fine. So the computers are involved. Such systems are flexible and they are easily upgradable. The technology of computers, such as networking, storage, you have printing extra, so you can easily share them, right? These are two technologies that we use for DSP. One is dedicated processor based DSP, next is a general purpose based DSP. So basic elements of DSP is first, see, since it's a digital signal processing, so it won't accept what analog signal, so you need to convert it into digital signal. Fine. So you need to convert it into a digital signal. So then you fed this digital signal into the digital signal processor. You get a digital signal output, fine, and followed by which d slash a will convert back your digital signal into analog signal. Right? So what this analog and digital converters, what they do, they generate an array of samples, sorry, they generate an array of samples and give it to the digital signal processor. So what they do, they just generate an array of samples and give it to the digital signal processor. Right? This array of samples or sequence of samples is digital equivalent of the input analog signal. Fine. So it's called the digital signal. The digital signal processor, this, it performs signal processing operations. So now what are signal processing operations? Like you have filtering, multiplication or transformation, amplification, etc. Now what are they are the operations over this digital signal sequence of samples and generate digital signal as it is. They are the operations over this digital signal and they generate another digital signal as its output. Now this digital signal processor can be the high speed digital computer or digital signal microprocessor. Such processors perform signal processing operations with the help of software which decide the type of operations that are used. Now the digital signal output from the digital signal processor is given to the digital to analog converter. Thus, digital to analog converter gets an analog equivalent of the output digital signal. So you get the analog output signal. So this is just what I have discussed in the previous slide. I just wrote it also down so that it will be clear to you what I was discussing. So now lastly we will discuss the classification of signals. So there are many signals. You have continuous signal, you have discrete time signals, you have analog signals, you have digital signals, you have multi-dimensional signals, fine. So followed by the numericals also. So I'm just trying to cover the theoretical portion for now. So the continuous time signals is you have a signal that is specified for every value of time. Can you think of an example? So it's specified for every value of time. You have audio, video recordings are continuous signals, continuous time signals. So I've also shown in the diagram. These are the continuous time signals. They are specified for every value of time. See, in continuous time, you look at next is discrete time signal. So here you only consider the time axis, that is the x-axis. This, see, amplitude is not considered. So this is important. See, there is always a difference between a continuous time signal and a discrete time signal. See, in continuous time signal, you always think of the that x-axis, that is time should be continuous. There should be no break in the time. Whereas in discrete time signals, you you also consider time only. That time should be discrete. You don't think of this amplitude axis, that is the x-axis, sorry, y-axis. You don't think of the this axis, so you don't think of the amplitude. You only consider the time axis. So time axis should be continuous. There should be no break in the time axis. Fine. What is an example of discrete time signal? You have monthly sales of corporation or stock market. These are all discrete time signals. So that is specified. A discrete time signal is specified only at discrete intervals of time. See, can let me ask you this: can an analog signal be a discrete signal? Yes, it can be. In analog signal, now you consider the amplitude. Now time is not considered. Now your amplitude should be a constant. Fine. Your amplitude should be present throughout the time axis. In continuous time signals, you consider the time axis. You consider the time axis. You consider the time axis. Fine. You consider the time. Whereas in discrete time, whereas in analog signals, you consider the amplitude. So your amplitude should be continuous. Here, time is not a constraint. Similarly, an analog signal can be also a discrete signal. When I will come to the class and give you a present lecture, right? Physically, I will present. That's important. So I will make a diagram of a signal which can be continuous as well as analog. So a digital signal is a signal which can whose amplitude can take only finite number of values, whereas analog signal is a signal whose amplitude takes infinite number of values, uncountable number of values. This is the basically difference. One thing should be clear: a discrete signal can also be an analog signal. Similarly, uh, a digital signal can also be a continuous time signal, right? Because in continuous time signal, you consider the time axis, whereas in discrete time signals, you consider the in this you consider the time axis, whereas in digital signals or analog signals, you consider the amplitude. So if amplitude is continuous, it's a it's the analog signal. If you have infinite number of uncountable number of amplitude values, fine, it's the analog. As well, it's the I hope it's clear. So rest we'll be discussing inshallah in the next video lecture, hopefully next week. Till then, assalamu alaikum and goodbye.